Tonight we're going to take a look at the smooth sort algorithm challenge presented by Topcoder. Now the smooth sort is a comparison-based sorting algorithm. It's a variant of heap sort, and it creates heaps like heap sort, but it creates heaps in a very specific manner. And it does this by creating something that can best be termed as a Leonardo heap, because each of the heap sizes are based off of Leonardo numbers. Now, Leonardo numbers are just a variant of the Fibonacci number system, and that's going beyond what we want to talk about right now. So we're just going to go ahead and go through the smooth sort algorithm. Now, the first thing that we need to do is we need to create some way to access the Leonardo numbers, because we're basing our heap sizes off of these numbers. So I decided to create the Leonardo numbers as a constant. Now I'm creating these Leonardo numbers by actually building a number generator that will yield the Leonardo numbers into an array. And this array is going to just be of size 25. So I'm actually going to get 25 Leonardo numbers, which will actually be quite a large set of numbers, which we don't really need, but we can actually see those numbers if we go ahead and run this file right now. And so we see this array of Leonardo numbers, and those are the numbers that we're using to basically just be designators for our heap sizes. Okay, so let me just clear that up real fast. Okay, so we have an idea of what our Leonardo numbers look like. As you can see, they're relatively based off of the Fibonacci number series, but they're built up a little bit differently. Again, rather than going into Leonardo numbers right now, let's actually go ahead and talk about the smooth sort. Now, the smooth sort itself, again, is that comparison-based sort that works similarly to heap sort, but it's dealing with smaller heaps, and if the heap is already sorted, it doesn't really worry about sorting those already sorted sections of the heap. And not only that, is if the heap's already sorted, it doesn't have to go back through the heap to double check to see that it's sorted. It just deals with it as is. So the main method creates an array called orders, and this order is just going to be which section or which heap it's going to be built into. And then the tree actually keeps that index value listed within those orders, because the order is just an array of those trees, and then those trees are the actual indices where that tree is going to be built. Then it runs through from 0 to the array length. Again, this is going to be designation of where in or which Leonardo heap each of these values is going to go into. And once it finds those values, then it will sift those numbers or values into the appropriate tree. And then going from right to left, then it does the same thing by making sure those numbers or those values are not only in the appropriate tree, but sifting them down into the correct order. So it does so by using two helper methods. The first helper method is the find and sift. Okay, so again, we're pulling the value from that array at the index, and then we are then using those Leonardo number values or those Leonardo numbers to put it into the appropriate tree with the appropriate size. So again, find and sift just takes the value, and while the tree and that tree is that index is greater than 0, it's going to find the parent index, which is the index minus the Leonardo number at order of tree, and it's going to then put it into the right or left index of that Leonardo tree. Then, once it does that, it's going to use the sift down method. So once the number is in the appropriate Leonardo tree, then it's going to sift that value down to its appropriate branch or leaf by using the sift down method. Again, the sift down method just takes that number, that value, and while the order is greater than 1, it's going to check to see if it belongs in the right or left index, or it's going to set values to the right or left index. And the right or left index are just smaller Leonardo trees, and then it's going to place it into the right or left branch or leaf of that value. Once it's done, it does it with so we do that twice, once with the left-hand index, once with the right-hand index, and then finally we are returned the array in its now new sorted order. All right, so let's go ahead and see that happen. So of course I've built into my normal testing method, or my normal testing block. So I create a shuffled array of 10 digits, and this time, because I have such large numbers that I want to play around with, I'm going from -1,000 to +1,000. So I create that random array and present it, and then I sort it using the smooth sort algorithm. So let me clear my screen one more time. We'll run the method itself. So Ruby in the library directory smooth sort.rb. So you see my random array here with numbers from -1,000 to +1,000, then returned in sorted order. So as you can see, it deals with negative numbers appropriately, it deals with positive numbers appropriately, and so it should also deal with 0 appropriately should 0 be used. And I don't know if we're going to get lucky enough to get a 0 in any of these tests. No, but that's okay, because then we can run the rspec. So let's go ahead and do that. So bundle exec rspec, and it's in the spec directory under smooth sort spec.rb. Go ahead and run that. We get 7 examples, 0 failures. It definitely handles 0 appropriately, and so that does it. So if there are any questions or comments, please post them to TopCoder in the forums, and I will answer them as soon as possible. Thank you.